The goal of this presentation is to provide the viewer with a basic understanding of condensation techniques used in air pollution control and various condenser capture devices. We will cover what is condensation and how do condensers work, types of condensers, and their design and components. Also their proper operating conditions, causes of decreased performance, and performance monitoring. In condensation processes, gaseous contaminants are removed from a gas stream by causing them to change to a liquid. In general, this can be accomplished by increasing the pressure or reducing the temperature, or by a combination of both. However, because of the cost of operating and maintaining compression equipment, most condensers for air pollution control use temperature reduction. The ultimate efficiency of a condenser depends on the operating temperature. As a vapor-laden gas stream is cooled, the molecules slow down and crowd together so closely that weak electrostatic forces between the molecules cause them to condense. The point at which this occurs is termed the dew point temperature. With further reduction in temperature, the vapor pressure of the condensing compound decreases. The lower the vapor pressure, the lower the concentration of the contaminant in the gas stream. Condensation systems generally operate at efficiencies greater than 90%. Three types of condensers are used for air pollution control: conventional systems, refrigeration systems, and cryogenic systems. Conventional systems are relatively simple devices that usually use air or water to reduce the gas stream temperature to as low as about 40 degrees Fahrenheit. Temperatures as low as 0 degrees Fahrenheit can be achieved using brine coolants. There are two categories of conventional systems: direct contact condensers and surface condensers. Direct contact condensers are essentially wet scrubbing equipment like spray towers or tray towers that directly contact the gas stream with a chilled liquid, usually water. The main advantages of contact condensers are their simplicity and low cost. The main disadvantage is the mixing of the condensed contaminants with the water, which increases wastewater treatment or contaminant recovery costs. The typical surface condenser is the shell and tube heat exchanger. These devices have a cylindrical shell that encloses numerous small tubes that run parallel to the cylindrical axis. The coolant, usually water or brine, flows through these tubes, while the gas stream flows through the shell outside the tubes. Baffles are typically used to cause the gas stream to make several passes across the tube bundle. Heat from the gas stream is transferred through the tubes to the coolant, reducing the gas stream temperature and causing the contaminant to condense. Another surface condenser is the tube and fin heat exchanger. In these devices, the contaminated gas stream flows through tubes that have several fins along their outside surface. Heat from the gas stream is transferred through the tubes and fins to an airstream that is blown across their surface, again causing the contaminant to condense. Surface condensers are more expensive to construct and to maintain than contact condensers. However, the collected contaminant is not mixed with the cooling fluid. Refrigeration systems use compressed coolants and operate at temperatures as low as minus 150 degrees Fahrenheit. The most common coolants use CFCs, although this is changing in response to the Clean Air Act amendments of 1990. The refrigerated liquid, flowing through tubes in a shell and tube heat exchanger, absorbs heat from the gas stream flowing on the shell side, reducing the gas stream temperature and causing the contaminant to condense. The absorbed heat causes the refrigerant liquid to change to a vapor. The refrigerant vapor is compressed and passed through a tube and fin heat exchanger, where the heat is transferred to air blown over the fins, converting the refrigerant back to a liquid. The compressed refrigerant liquid flows through an expansion valve to reduce its pressure and then returns to the condenser. To prevent the accumulation of ice, the gas stream usually passes through a shell and tube heat exchanger maintained at about 40 degrees Fahrenheit to condense any moisture before it enters the low-temperature condenser. Cryogenic control systems use liquefied gases such as nitrogen and carbon dioxide to obtain temperatures as low as minus 320 degrees Fahrenheit. These systems are relatively simple since no refrigeration unit is needed and the coolant is vented to the atmosphere. In the simplest cryogenic system, the liquefied gas, flowing through tubes in a shell and tube heat exchanger, absorbs heat from the gas stream, flowing on the shell side, reducing the gas stream temperature and causing the contaminant to condense. The absorbed heat causes the liquefied coolant to change to a gas, which is discharged to the atmosphere. At these extremely low temperatures, it is possible for the contaminant to accumulate as frost on the exterior surfaces of the tubes. To avoid this problem, it may be necessary to operate a parallel heat exchanger. One heat exchanger would be defrosting, while the other is in service. Another solution is a dual heat exchanger system. In the first heat exchanger, the liquefied gas is used to cool a circulating heat exchange fluid to a temperature just above the freezing point of the contaminants. This fluid flows to a second heat exchanger, where it is used to condense the contaminants, and then returns to the first heat exchanger. Liquefied gases can also be used in direct contact systems. These systems also avoid the frosting problem, since there are no surfaces at extremely cold temperatures. The liquefied gas is injected through spray nozzles into an open chamber, where it directly contacts the contaminated gas stream. The chamber is insulated to keep the temperature as low as possible. Strip heaters may be mounted on the exterior of the chamber walls for the occasional removal of any accumulated frost from the interior surfaces. One application of condensers is in the steam stripping of wastewater to remove organic compounds. The contaminated wastewater is directly contacted with steam in a countercurrent tray tower. The volatilized organics and any uncondensed steam are collected from the tower and condensed in a water-cooled shell and tube condenser. The recovered condensate is separated in a decanter to recover the organic compounds, which are either returned to the process or incinerated to recover their energy value. The non-condensable organics exiting the condenser are usually incinerated. To review, the common types of air pollution control condenser systems are conventional, both direct contact and surface condensers; refrigerated; cryogenic. Condensers can have heat exchange methods such as direct contact heat exchangers, shell and tube heat exchangers, tube and fin heat exchangers, parallel heat exchangers, and dual heat exchangers. The capture efficiency a device has in changing gases to a liquid condensate is affected by temperature and vapor pressure. There are several factors that contribute to loss of performance in condensers. These problems include high outlet temperature, low coolant flow rate, reduced heat transfer efficiency, buildup of ice or frozen organic compounds. The ability to evaluate performance problems during a field inspection will depend on how well the system is instrumented. Most refrigeration systems and complex cryogenic systems will have sufficient instrumentation for an adequate evaluation. However, simpler systems may have limited instrumentation. Performance evaluation of these systems will be difficult unless measurements of important parameters are made. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced collection efficiency. The most direct measure of the performance of a condensation system is the organic vapor concentration in the outlet gas stream. However, most condensation systems do not have permanently installed analyzers. If there is an analyzer, the adequacy of the data should be checked as part of the overall performance evaluation. This would include an inspection of the condition and integrity of the sampling system, and a check of the sample gas flow rate. In addition, the calibration frequencies and procedures and the maintenance records of the instrument should be checked. Calibration should be performed on a daily basis using a calibration gas cylinder that is less than 6 months old and has a pressure of at least 150 psig. Portable analyzers should not be used to evaluate condenser performance. Condensation systems are often used on sources that generate high organic vapor concentrations. It is possible that during malfunctions of the system, the outlet gas stream concentration could be in the explosive range. Static electricity on the instrument probe could be a source of ignition. The best indicator of the performance of a condensation system is the outlet gas stream temperature. Since the outlet concentration is equal to the vapor pressure at that temperature, increased outlet gas temperature would indicate reduced collection efficiency. If outlet temperature records are maintained, they should be reviewed to determine periods of increased temperature. Short-term increases are usually associated with frost removal, and the records can be used to determine the frequency. A gradual increase in outlet temperature will occur if ice or frozen organic compounds are accumulating on the heat transfer surfaces. The coolant flow rate and the coolant inlet and outlet temperatures can be used as direct indicators of the condenser system performance. Reductions in the coolant flow rate or reductions in the temperature difference across the condenser indicate reduced heat transfer, reducing the collection efficiency. Decreased gas flow rates will result in reduced capture of the contaminants at the source, resulting in fugitive emissions. Low gas flow rates may result from the buildup of ice or frozen organic compounds in the condenser. Decreased fan motor currents and decreased hood static pressure indicate a decrease in the gas flow rate. To review, to determine if a condensation system is working properly, field personnel should observe, if possible, the outlet gas stream, VOC concentration, but not likely available. The outlet gas stream temperature, which is more likely available. Indirect indicators of efficiency include the coolant flow rate and the coolant inlet and outlet temperatures. Decreased gas flow rates will reduce the capturing of the contaminant. As with any inspection of an air pollution control device, attention must be given to the system's records and physical condition, and compliance with applicable rules. Condensation systems used for air pollution control have many safety considerations, including inhalation hazards, explosive hazards, and cold surfaces. Further training and experience will be necessary to complete all field tasks safely.